Hi, welcome to lecture 18. We've almost entered the realm of topology. So let's just recall. So maybe again from topology. So given a sequence, let's say xn in Q, we say it is Cauchy with respect to, or it's a Cauchy sequence with respect to the p-adic absolute value if for all epsilon larger than 0 there exists a natural number say n epsilon such that the difference between xn and xn, the p-adic absolute value, is less than epsilon whenever n and n are larger than this natural number n epsilon. Okay, so this is what it means for the sequence to be Cauchy, and we say this the sequence is convergent converging to L. Again, almost an identical definition. For all epsilon larger than 0, there exists a natural number n epsilon such that the difference between x n and L, the p-adic absolute value, is less than epsilon for all natural numbers that are larger than this n epsilon. Okay, so convergent sequence, and we are going to play around with this Cauchy sequence and convergent sequences. So the first thing that we want to show is that the addition map is a map on Q cross Q to Q, since Cauchy sequences in Q cross Q to Cauchy sequences in Q. Again, it's just playing around with things similar to how you might have played around with the usual Archimedean absolute value. So if you have a Cauchy sequence in Q cross Q, and what we want to show is that the sum, this new sequence xn plus yn, is a Cauchy sequence in Q. Okay, so just unraveling what it means to have a Cauchy sequence in Q cross Q. So given an epsilon, there exists an n epsilon such that, you know, the nth term xn comma yn and the nth term xm comma ym, the distance between them is less than epsilon whenever n and m are larger than equal to n epsilon. And how was the distance function defined on the product? So it was the max of, we take the difference of the p-adic absolute values in the first coordinate, we take the difference in the second coordinate and take the p-adic absolute value. So this was by definition how the distance function was defined on the product, and so this is less than epsilon whenever n and m are larger than n epsilon. And so observe that if you do take two numbers that are larger than this n epsilon, now we want to show that the sum xn plus yn forms a Cauchy sequence. So let's try to unravel what that means. So you take the distance between xm plus ym and xn plus yn, which is xm plus ym minus xn plus yn in the p-adic absolute value, and if you just collect the xn's and ym and yn, and then you use the ultrametric property, what we have is that this is less than equal to the maximum of the p-adic absolute value of the difference but we just saw earlier that the maximum of the difference between xn and xm in p-adic absolute value and yn and ym in the p-adic absolute value of yn minus ym, this is less than epsilon whenever n and m are larger than or equal to n epsilon. So this quantity here, this last quantity that we wrote down is the same quantity here, and so it must be less than epsilon. Okay, and so we've just shown that this is just the same thing as showing that xn plus yn is a Cauchy sequence in Q. Okay, so this proves the proposition that addition takes Cauchy sequences to Cauchy sequences. Okay. Definition, we will say that a sequence is a null sequence if the limit as n goes to infinity of xn in the p-adic absolute value, this is 0. Okay, so in other words, the sequence xn is a convergent sequence converging to 0. Okay, I'm just using the fact that the absolute value of xn is nothing but the absolute value of xn minus 0. Okay, and so in other words, given any epsilon, there exists an n epsilon such that the absolute value of xn is less than epsilon for all n larger than or equal to n epsilon. A simple observation, so all convergent sequences are Cauchy, so in particular a null sequence xn is a Cauchy sequence, and you can also check this directly. So given an epsilon, so we have an n epsilon such that the p-adic absolute value of xn is less than epsilon whenever the natural number that you choose for the index is larger than n epsilon, and therefore the sequence xn must be a Cauchy sequence since, you know, for all n larger than or equal to the same n epsilon, so you take any n and m, you take the difference between xn and xm and compute the p-adic absolute value by the ultrametric property. What we have is that it's less than or equal to the maximum of the p-adic absolute value of xn and the p-adic absolute value of xm, but each of these quantities because the index n and m are larger than n epsilon, each of the quantities are less than epsilon. So the maximum is also less than epsilon. And so this shows that the sequence xn, if it's a null sequence, it must be Cauchy. Okay. So here's a lemma that's actually going to be a good exercise in computing negations of statements. So suppose you have a sequence xn, it's a Cauchy sequence that is not a null sequence. Then there exists a natural number, let's call it n naught, says that for all natural numbers larger than this n naught, we have that the p-adic absolute value stabilizes. And in particular, it's not zero. Okay. Now, since this xn is not a null sequence, so we define what it means for a sequence to be a null sequence. So now we just have to define what it means for a sequence to not be a null sequence. So as I said earlier, it's just an exercise in negating that statement. So there must be some positive epsilon naught such that for all natural numbers n, there exists an Rn that's larger than or equal to n with the property that the p-adic absolute value of this xRn is larger than or equal to epsilon. Okay, so that's the first fact that you get from the hypothesis that xn is not a null sequence. But another hypothesis is that the sequence xn is Cauchy. So since the sequence xn is given to be Cauchy, there exists an n epsilon naught such that if you take the difference between xn and xm and compute the p-adic absolute value, this is less than epsilon naught whenever the indices n and m are chosen to be larger than n epsilon naught. Okay, and so what's the claim? So I need to find this n naught in the proposition where the p-adic absolute value stabilizes. Okay, so the claim is that for all n which is larger than this r and epsilon naught, and just for simplicity we'll call this r naught. So we have that the p-adic absolute value of all the xn's equals the p-adic absolute value of this xr naught. Okay, so this claim complete the proof of the lemma. So why is the claim true? Now observe that if n is larger than r and epsilon naught, which was what we call r naught, by construction this Rn is larger than or equal to n. So this little n, if it's larger than or equal to r naught, it must be larger than n epsilon naught. Okay, so just observe. So if n is larger than or equal to r naught, then n must be larger than n epsilon naught, since r naught, which is r n epsilon naught, is larger than n epsilon naught. Okay. So for all n which is larger than this r naught, you take xn and compute its p-adic absolute value, and you play this trick of subtracting and adding x r naught. Okay, and then use the ultrametric property. So this is less than equal to the maximum of the p-adic absolute value of the difference between xn and x r naught and x r naught. Okay. On the one hand, since n is larger than r naught, which is larger than n epsilon naught, we have that xn minus xn r naught and p-adic absolute value should be less than epsilon naught. But on the other hand, we have the construction that x r naught is larger than or equal to epsilon naught. So this first quantity here is less than epsilon naught, and the second quantity is larger than or equal to epsilon naught. So the maximum between them is just x r naught, the p-adic absolute value of x r naught. So thus the maximum between these two quantities is the p-adic absolute value of x r naught. Okay. So that's our first inequality. Now let's play the same trick, reversing the roles of xn and x r naught. So again, for all n larger than r naught, larger than or equal to r naught, if you take the p-adic absolute value of x r naught and you play the same trick of subtracting and adding xn this time, and again using ultrametric properties, now what do we have? We have the max of the p-adic absolute value of the difference x r naught minus xn and the p-adic absolute value of xn. Now on the one hand, we know that x r naught minus xn, since n is larger than or equal to r naught, which is larger than n epsilon, we have that x r naught minus xn, the p-adic absolute value of that is less than epsilon. Okay, so the question is, can the maximum of these two quantities, can it actually equal the difference between x r naught and xn in the p-adic absolute value? But we know that to be less than epsilon naught. So if this were true, what would we get? We would get that the absolute value of the p-adic absolute value of x r naught is strictly less than epsilon naught, but this contradicts the fact that by construction the p-adic absolute value of x r naught was larger than or equal to epsilon naught. Okay, so whatever we assumed here, the maximum of these two quantities, cannot be the first term, it has to be the second term. So thus the maximum of x r naught minus xn in p-adic absolute value and the p-adic absolute value of xn must equal the p-adic absolute value of xn. So in other words, if we combine this equation with this observation, we get that the p-adic absolute value of x_r naught is less than equal to the p-adic absolute value of xn for all n larger than r naught. Okay, so this gives us a reverse inequality. So we have on the one hand that the p-adic absolute value of xr naught is less than equal to the p-adic absolute value of xn, and on the other hand we have already shown that the p-adic absolute value of xn is less than equal to the p-adic absolute value of xr naught. So combining these two inequalities, we get that the p-adic absolute value of xr naught equals the p-adic absolute value of xn for all n larger than equal to r naught. And this completes the proof of the lemma. Okay, and again a nice exercise that we'll use a little later, but the proof of this exercise is, or the solution to this exercise is identical to the proof of the above lemma. Suppose you have a convergent sequence with, let's say, the limit as n goes to infinity. So let's say the sequence converges to, say, x naught. So usually this is denoted by saying that the limit as n goes to infinity of xn equals x naught. And suppose that this limit is not 0. So in particular this convergence sequence is not a null sequence, then there exists an n naught such that for all natural numbers that are larger than n naught, we have that the p-adic absolute value of xn equals the p-adic absolute value of the limit for all n larger than n naught. So I should add that in the previous lemma there is one exercise for you that's remaining. So exercise for the students. So show that this xr naught is in fact not 0. Okay, and just use the fact that the p-adic absolute value of xr naught is in fact larger than equal to epsilon naught, which is larger than 0. So the simple observation would complete the proof of the lemma, but I just realized now that I didn't mention this. Okay. So on to the next proposition, proposition 45. We'll show that the inversion function, it sends alpha to alpha inverse, is continuous. Again, the proof is it's enough to show sequential continuity. So consider a convergent sequence xn with the sequence converging to, say, x naught in Q cross. And what do we want to show? That if you take the limit as n goes to infinity of xn inverse, this converges and its limit equals x naught inverse. Okay, so again the game is to look at the difference between xn inverse and x naught inverse. So this is 1 over xn minus 1 over x naught, and then if you just collect denominators, then the numerator is x naught minus xn. Again, by the previous exercise, since this x naught belongs to q cross, this x naught cannot be 0. So we must have an n naught such that the absolute value, the p-adic absolute value of xn and the p-adic absolute value of the limit, they are equal whenever you choose an index n that's larger than n naught. Okay. And now I choose an epsilon 1 for the time being. That's epsilon times the p-adic absolute value of x naught square. Okay, so why I make this choice will be clear in a moment, but it's motivated by this expression above. And I choose my natural number to be the maximum of this n epsilon 1 and n naught. Okay. And so then for all indices n that's larger than n prime, what do we have? So I want to compute xn inverse minus x naught. I want to show that xn inverse is a convergence sequence that converges to x naught inverse. So I compute the difference and compute its p-adic absolute value. And we just saw that this is x naught minus xn over x naught times xn. We want to compute its p-adic absolute value. The p-adic absolute value is multiplicative. Okay, but since the index is larger than n prime and n prime is larger than n naught, so we have that under these cases the absolute value of xn is nothing but the p-adic absolute value of x naught. So whenever your index is larger than n prime, it's larger than n naught. So in fact the p-adic absolute value of xn turns out to be nothing but the p-adic absolute value of x naught. So the denominator just becomes the p-adic value of x naught square. Okay, but since I've chosen my n prime to be larger than n epsilon 1, for all n larger than n epsilon 1, we have that this is the numerator is less than epsilon 1 divided by x naught, the p-adic absolute value of x naught square. But what's epsilon 1 is just epsilon times the p-adic absolute value of x naught square. So that's why I chose this weird looking quantity, and you just get epsilon. Okay, so we've shown that the sequence xn inverse is convergent and it converges to x naught inverse. Okay, so this proves the proposition. Okay, and now one final fact from topology. So if you have a Cauchy sequence, and again this is not hard to show, so if you have a Cauchy sequence in Q, then there exists a uniform bound B, and you can choose the bound to be positive on the sequence. That is the p-adic absolute value of any member of the sequence is less than or equal to B for all indices n. Okay, so I've said that this is a fact from topology, but it's not hard to show. I'll use this fact for the next proposition, proposition 46, that multiplication since Cauchy sequences in Q cross Q to Cauchy sequences in Q. And again, the proof is very similar to the proof for the addition function. So suppose you have a Cauchy sequence, let's say xn yn in Q cross Q. Again, what does that mean? So let's try this as we have a Cauchy sequence in Q cross Q. And again, the distance function on Q cross Q is given by, so if you take an arbitrary element xn yn and xm ym, the distance function, you take the difference of the first coordinates, compute the p-adic absolute value, take the difference of the second coordinate and compute the p-adic absolute value, and take the maximum and supremum. And for the sequence to be Cauchy, what it means is given any epsilon or epsilon prime, there exists an n epsilon prime such that for all natural numbers, for all indices that are larger than this n epsilon prime, we have that this distance, which is given by this function, this maximum. So this maximum of xn minus xm in p-adic absolute value and yn minus ym in p-adic absolute value, this is less than epsilon prime. Whenever you choose n and m to be larger than an epsilon prime. But this left hand side is the maximum of the difference between xn and xm in p-adic absolute value. And you compute the difference between yn and ym and take the p-adic absolute value. And so in particular, the difference between xn and xm in p-adic absolute value is less than this maximum. The difference between yn and ym in p-adic absolute value is also less than this maximum. So in particular, what we can see is that the sequence xn and the sequence ym, these are also Cauchy sequences. These are Cauchy sequences in Q. And so let say bx and by be the uniform bounds on these Cauchy sequences. And note that these bounds are chosen to be positive. Okay. And again, what do we want to show? So what we want to show is that the sequence xn times yn is a Cauchy sequence in Q. So again, as earlier, what we want to do is you want to consider xn yn minus xm ym, and then again you play this trick of adding and subtracting some quantity, and this time it's xm yn plus xm yn. And then if you factor out the right quantities, you get xn minus xm times yn plus xm times yn minus ym. And now you just have to play this game with triangle inequalities. So choose epsilon 1 to be, let's say, the maximum of epsilon over bx and epsilon over by. And again, what we have is that for all little n and little m that are larger than an epsilon 1, we have, so if we take the difference xn yn minus xm ym and compute the p-adic absolute value, so it's this expression here. So this is nothing but xn minus xm times yn plus xm times yn minus ym in p-adic absolute value. And then again you use the allometric property plus use the fact that the p-adic absolute value is multiplicative. So you get xn minus xm in p-adic absolute value times the p-adic absolute value of yn. And the second quantity is the p-adic absolute value of xm and the difference of yn minus ym in p-adic absolute value. Okay. And so the way we've chosen n and m, the difference between xn and xm, remember that if n and m are chosen to be larger than or equal to n epsilon prime, then the difference between xn and xm in p-adic absolute value is less than epsilon prime. The difference between yn and ym in p-adic absolute value is less than epsilon prime. So we've already shown this. So the difference between xn and xm in p-adic absolute value is less than epsilon 1. The p-adic absolute value of yn, since yn forms a Cauchy sequence, we have this bound by. And then similarly, we have this bound bx for the p-adic absolute value of this Cauchy sequence xm. And again, similarly, yn minus ym in p-adic absolute value is always less than epsilon 1. But you see, the way we've chosen epsilon 1 times bx will always be less than or equal to epsilon, and epsilon 1 times by will always be less than or equal to epsilon. So both of these quantities will be strictly less than epsilon. So just playing around with these choices of epsilon 1, by and bx, we get that the p-adic absolute value of the difference xn yn minus xm ym is strictly less than epsilon. And this proves, so this is true for all n and m larger than n epsilon 1, and so this proves that the sequence xn yn is Cauchy. And this completes the proof of the lemma proposition. Thank you.